Can somebody remind us what we're doing? What's the last thing we did? Anybody? Just to bring your minds back from wherever they've gone over the weekend. Yes?
Kind of combining functions and sequences.
Combining functions and sequences, yeah. So we're basically saying that if your sequence is basically a function that you know in disguise, right? So you have some sequence, but really this sequence is, you have some sequence is of n, right? But really there's some function that you know where the function takes on those values at the natural numbers. Okay, so in fact this was some function that you knew. Then so you have a sequence a sub n, but also you have a function f, and f of f sub n is a sub n. Then if the limit of f of x as x goes to infinity equals some number, right? And this is something that I hope you should have seen in Calc 1, right? The limit of a function as the variable goes to infinity. If that limit exists, right? So if your function's limit actually exists, then the limit of then your sequence, right, converges to L also. Okay. Then your sequence converges to L also. Okay. So we said that one thing that we could do with this was to use L'Hopital's rule. One kind of cool thing. So here's an example. If I take the limit of 1 plus 1 over n to the n as n goes to infinity, the limit of 1 plus 1 over n to the n as n goes to infinity. This is something that we threw out as a question at the beginning, and we said it kind of balanced out at e. Okay, and the way we're going to see that, so this actually turns out to be e, and the way we see that is to look at the function. So consider the function f of x being 1 plus 1 over x to the x. Okay, 1 plus 1 over x to the x. Okay, and then if you look at the limit of this guy, well, the limit of 1 plus 1 over x to the x as x goes to infinity, what is that? This is a so-called indeterminate form, right? Do you see what's going to happen to it? As x goes, the same thing that happened to this guy, right? As x goes to infinity, the thing in the parentheses becomes 1, right? And the exponent becomes infinite, right? So this becomes 1 to the infinity, right? Which I'm hoping that at least some of you have seen when you did L'Hopital's rule. Does anybody remember how to do it? How to do this sort of thing with L'Hopital's rule? You need to bring in another function. Anybody remember? Yes?
I just have a question.
Yes, okay.
Why would it be 1 to the infinity?
It's not really 1 to the infinity, that's why it's in quotes. But it looks like it's something like 1 to the infinity, right? Because as x becomes infinite, this 1 plus 1 over x basically becomes 1, right?
Right.
And this x here becomes infinite. Okay, there's no such thing as 1 to the infinity. Okay. Let me just erase that. Okay, but it's what's called the indeterminate form 1 to the infinity. Anybody remember? Should I offer a bonus point on the exam to the person who remembers the function? Franco?
Natural log.
Natural log. And so you guys are just waiting for this bonus point to come out, and then you give me the answer. I should stop giving you bonus points. That's the moral. You're only going to do it unless you get a bonus point. It's like a capitalistic society. Okay, yeah. So use the natural log. So you say, okay, I want to get the limit of this thing, but I don't know how to get it, so I take the natural log of it. So I want this, right? This is what I want, right? Let's call this, I want this thing, but I don't know how to get it. So I take the natural log of it, okay? I take the natural log of it. Natural log is continuous. I can pass the natural log through if the limit turns out to exist, and it will. Okay, so I get the natural log of the limit of the natural log, right? I can switch the order, natural log and limit, right? I end up with, I can pull the x down because of the properties of the natural log, right? Infinity, right? And so you end up with this thing, right? Which is, again, an indeterminate form, what people call infinity times 0, right? With infinity times 0, generally what you do is you, what do? Those of you who remember L'Hopital's rule? One thing you could do is bring this thing to the bottom, right? You can bring this thing to the bottom, and you get natural log of 1 plus 1 over x over 1 over x as x goes to infinity. Okay. Right? And now you see it's in 0 over 0 form, right? Okay. So take 1 minute and evaluate it using L'Hopital's rule. Apply L'Hopital's rule to it. See what happens. Okay, turn to somebody nearby, tell them what happens. Okay, somebody want to tell me what you get? What do you get? What do you get? You differentiate the top and the bottom. What happens when you differentiate the top? Natural log of something. Natural log of a function. When you differentiate it, what do you get? You get what? 1 over f prime x, right? By the chain rule, right? So you get 1 over 1 plus 1 over x, right? Times the derivative of that, right? Which is what? Negative 1 over x squared, right? Right? The derivative of the bottom, also negative 1 over x squared, right? Those guys cancel off, right? As x goes to infinity, you get
x over 1 plus x.
As x goes to infinity, what happens here? You get 1, right? 1.
Yeah.
Okay, right? And so, is okay?
Yeah.
Okay, good. Okay. Everybody all right? Any questions? Any questions? Yes, Ben.
That was supposed to approximate to the
We're not done yet. We're not done yet. Are there questions about what we've done so far? Okay. So we get this, that this thing equals 1, right? This thing equals 1. Okay. The natural log of the thing that we're trying to figure out is 1. Okay. Okay. That means that the thing that we're looking for turned out to be e to the 1, right? So this is e. This is going to be e to the 1, namely e, right? The natural log of it, this is the thing that we wanted, right? This is the thing that we wanted. The natural log of that thing we wanted turned out to be 1, right? So the thing that we wanted is going to be e to the 1, right? Right. If its natural log is 1, then it must be e. Okay. So that's what we got. This thing turned out to be e. Julia, question? No? Good. Okay. Okay. So this is just another example of how one uses that fact that. We said last time that if your sequence is a function, then if the limit of the function exists, then the limit of the sequence exists. So just another example of using L'Hopital's rule. And I threw it in just to remind you about this business of this kind of indeterminate form. Yeah, Chandler.
Well, taking the natural log always turn out so that or is it the case where that x1 equals a variable?
Well, so this was the so-called 1 infinity form, right? If it's this kind of indeterminate form, then yes, the natural log is what you want to use on it. So that's just one final example of that stuff. We're still in section 8.1. 8.1 for some reason is huge. I think we'll get out of it today. So there's one more idea in 8.1, and it's called monotonic sequences. Monotonic sequences. Okay, so we first start off with something called bounded sequence. Okay, so this is not, we haven't gotten to monotonic sequences yet, but we'll get there in a second. Okay, so first idea is something called a bounded sequence. Okay, so here's the definition. What do you think a bounded sequence ought to be? From the word bounded, what do you think a bounded sequence should be? Anybody make some guess as to what it is? Elizabeth?
Does it it has a beginning and an end, like a sequence between 1 and 7 or something?
So it's not a sequence that finishes. Do you mean a sequence that sort of stops?
Yeah.
No, so that would be what's called a finite sequence rather than an infinite sequence. Okay, but Bea?
like a sequence that stays within like a range.
Mm-hmm. So a sequence that stays within a particular range. Like the outputs stay between one value and another value. Okay, so a sequence that doesn't go off to infinity, either up or down. Okay, so that's the idea. Here is the mathematical definition. If there exists a number, m, such that the absolute value of your sequence is controlled by m for all n, then we call a sub n a bounded sequence. bounded sequence. Okay, so here's the picture. What this is saying is that there's some number m, and the absolute value of your sequence is controlled by m. In other words, your sequence lives between negative m and positive m, right? All your values lie between negative m and positive m, right? That's what this is saying. If there's some number and all your values stay between negative that number and positive that number, then we call this thing a bounded sequence. Okay. There are also sort of intermediary ideas. So there's the notion of bounded above, or bounded below. Right? You can probably guess what these mean, right? Bounded above means that there's an upper number, but not necessarily a lower number. Right? There's an upper bound, but not necessarily a lower bound. Bounded below means that there's some lower bound, but not necessarily an upper bound. Okay. Right? Like, so bounded above would mean that there is some upper number m, and all your values are below that m. Okay. All your values are below that m. So m, right? So this is bounded above. Right? There exists m such that a sub n is less than m for all n. Now I'm starting to pile on the mathematical symbolism, but I hope you can read it. There exists an m such that a sub n is less than m for all n. Okay, everybody all right with that? In which case, we call m an upper bound. Okay. Take 10 seconds and write down what I'm going to write over there for bounded below. Show the person next to you the string of symbols he wrote. Okay. It'll be, I hope, he wrote something like this. There exists an m such that a sub n is greater than or equal to m for all n. Typically, you could have used the big M here also, but typically one uses a little m for the lower bound, the lower bound, and a big M for the upper bound. It doesn't matter, right? And in which case we call little m the lower bound, or a lower bound of sequence. Right? So you have some sequence, and it's going upwards, say, right? And then this little m would be its lower bound, right? And you notice that I said a lower bound, not the lower bound, because you can have many lower bounds, right? All these, anything lower than your lower bound is still a lower bound, right? Okay, so these are pretty simple ideas, right? You've got an upper bound, lower bound, right? Your sequence is bounded. If your sequence is bound, let me ask you this. If your sequence is bounded, does your sequence have a limit? Does that force your sequence to have a limit? Suppose your sequence is bounded. Must it have a limit? Okay, how many people say yes? Must have a limit. Bounded implies limit exists. Yes, no. How many people say yes? A couple people say yes. How many people say no? More people say no. Those of you who say no, give me an example of something where it's bounded but no limit exists. How you know?
Like -1 to the end.
-1 to the end. Okay, yeah, that's bounded. That's bounded. But you see that there's no limit, right? Okay, what about the other way? The limit exists. Does that mean that it's bounded? If your function has a limit, I'm sorry, if your sequence has a limit, must it be a bounded sequence? Okay, vote again. Who says limit implies bounded? Yes? Few people? No? Fewer people? Some people? Okay. The answer is yes. That if a limit exists, then it's going to be bounded. Can somebody sort of give their intuition as to why that would happen? Anybody want to say why they thought that? Because there were a few of you who said it. You must have had some idea about it. Yeah, Elizabeth.
Well, if the sequence is approaching a limit,
Yeah.
let's say it's like 5,
Sure.
and that's the highest value it ever is, that would be maybe like the upper limit. Or alternatively, if that's lower than like the value for maybe 1, you could just find the highest value, and that would be the upper limit. I don't know. If it has a limit,
If it has a limit, then
it has to have one highest value.
there will be one highest value.
Yeah, and one lowest value.
Okay. So yeah,
Kind of.
you can sort of see why that's going to happen, right? Like you say, well, look, my sequence is going to become really close to 5, right? I know that if I set some tolerance, then past some point, everybody's within those bounds, right? Past some point, maybe n equals 100, or maybe n equals 10, everybody's within those bounds, right? So those guys are definitely bounded, right? Past this point, past 10, everybody's bounded, right? Yes? Right? And then the guys before, there's only 10 of them, right? There's only 10 of them, so you just, look at the biggest guy, right? And that's the bound for those early guys. Or look at the smallest guy, and that's the lower bound for those guys. Those guys are also bounded, right? The biggest one of them is their bound. The lowest one of them is their bound, right? So these guys are bounded. These guys are bounded. Well, they're all bounded, right? They're all bounded above, and they're all bounded below. Okay, so that's the idea. Okay. Yeah. Yes, Elizabeth.
Is the tolerance, like in the definition of a limit of a sequence, is the tolerance like related to why it's bounded? Like if you just increase the tolerance to the upper and lower bound?
But you can't assume that there's an upper and lower bound first,
Oh, okay.
right? So like, you don't know that there is an upper and lower bound to begin with. So you can't logically go that way. Yeah. Yeah. Right. So let me just sketch out how you would sketch of the argument why this thing convergent implies this thing is bounded. Okay. Right. So you'd say, well, look, this thing converges, so if a sub n converges to are all a sub n satisfy that a sub n minus L is less than 1 for n past some capital N. I'm just saying what I said here, right? If your sequence converges to some limit and take your epsilon to be 1, you know that everybody beyond this point is within. In other words, right, all a sub n satisfy a sub n are between L minus 1 and L plus 1 for n bigger than n. Right? So those guys are bounded. Right? For n less than n, there are only finitely many. Right? There's A1, A2, through an minus 1. There are only finitely many elements of your sequence. Right? So these are clearly bounded. Right? They're bounded above and below. Just take the largest one, that'll be your upper bound. Take the smallest one, that'll be your lower bound. The largest is the upper bound. Smallest, the lower. Right? So the guys before n are bounded, the guys after n are bounded, so they're all bounded. Okay. Since the A1 through AN minus 1 are bounded, and the AN for n bigger than n are bounded, the whole sequence is bounded. This is just the just writing down the idea. But if you understood what we said over here, that's basically all I want from you. I don't expect you to reproduce this argument. Okay. I'm just writing it down. Anna.
Where did you write there are finitely many what?
Elements, sorry. Elements. There's only finitely many elements of your sequence. These are clearly bounded. The largest is the upper bound, the smallest the lower. Okay, any questions on the idea? Any questions on the idea? Hannah?
I'm sorry, but can you read the last part? Some.
Sorry. Since the A1 through AN minus 1 are bounded, and the AN for n bigger than n are bounded, the whole sequence is bounded. The whole sequence is bounded.
Thank you so much.
You're welcome. Okay, any questions on the idea? Right? As long as you get this idea, I'm happy. That's all I expect of you. I know you don't have to write down this proof. You know, the idea is writing down the proof. That's for a later night. Okay, so that's all we want to say about bounded sequences so far. What is a bounded sequence, right? Means you have a, it's trapped between lower and upper guys, right? And this fact that if you're convergent, then you're bounded. If you're convergent, then you're bounded. Okay. Okay. So now we're going to talk about what are monotonic sequences. So monotonic sequences. Okay. So here follow a bunch of sort of obvious definitions. If a sub n is less than or equal to a sub n plus 1 for all n, we call a sub n an increasing sequence. So sort of obvious, right? The values only get bigger. They either stay the same or get bigger. Okay, if it's strictly bigger, then we call it strictly increasing. Okay, if it's like this, if a sub n is less than a sub n plus 1 for all n, then we call it strictly increasing. Strictly increasing. Right? And then I'm going to define decreasing and strictly decreasing. Okay, but you can write down those for yourself. Okay, everybody all right? Simple, right? These are, nothing intimidating. You have a sequence and it's getting bigger. We call it an increasing. In this case, the thing I've drawn, it's strictly increasing sequence. Okay. Of course, if you are strictly increasing, then you're increasing, right? It's just a tighter condition. Okay. And here's the definition. If you are any of 1 through 4, we call you monotonic. Monotonic sequence. Okay. If you're an increasing sequence or you're a decreasing sequence, strictly or non-strictly, then we say you're monotonic. I'm sorry?
You said, so if you're just strictly increasing or strictly decreasing, you're monotonic.
If you are any of these guys, if you're increasing strictly, if you're increasing or decreasing strictly or non-strictly, you're monotonic. Right. So if you're an increasing sequence, you're monotonic. If you're a decreasing sequence, you're monotonic. So here's an example. A sub n is 2 to the n over n factorial. Take a minute and tell me if this is increasing, decreasing, what is this? I think we've seen this guy before, so it should be familiar. turn to somebody nearby, tell them what it is. Okay. What is it? What is it? It's what? Increasing? I don't think so. Is it decreasing? Yeah, it's actually decreasing. Is it strictly decreasing? No? So let's see. A1 is 2 over 1. A2 is 2 squared over 2 factorial. Which is 2 again, right? A3 is what? 2 cubed over 3 factorial, right? 8 over 6, right? A4, etc., right? So you see that, well, at least from looking at it, it seems like it's a decreasing but a not strictly decreasing sequence, right? If you wanted to be a bit more careful about it, you'd say, let's compare an plus 1 and an. Okay, right? An plus 1 is 2 to the n plus 1 over n plus 1 factorial, right? An is 2 to the n over n factorial. Right? And so you see that a n plus 1 is a sub n times 2 over n plus 1. Right? A n plus 1 is a n times 2 and divided by n plus 1. Right? If I multiply this guy by 2 over n plus 1, I get a n plus 1. Right? Okay. And so what you see is that past, past a certain point, right? As long as I'm beyond n equals 1, then this is strictly decreasing. Okay. So this is actually strictly decreasing for n greater than or equal to 2. Okay. If I start at 2 and go onwards, then it's a strictly decreasing. But if I'm just looking at the whole sequence, it's just decreasing for n. It's decreasing, right? This is a decreasing sequence, but if I look at past a certain point, then it's strictly decreasing, right? Because I'll always be multiplying by something smaller than 1. Right? Okay. Here's another example. A sub n equals n over e to the n. What do you think about this? Increasing? Decreasing? Just look at it. What do you think is going to happen? N over e to the n. Okay.
Is it strictly decreasing?
Strictly decreasing, and why do you think so?
Because for every value of n, it's gonna decrease.
You said the same thing twice.
Essentially.
It's okay.
If a sub n is less than a sub n plus 1 for all values, but strictly decreasing.
Now you've said the same thing 3 times. Okay, so I want you to tell me why you think this is decreasing. Why you think it's decreasing, right? Not that it is decreasing, which you said. Why do you think this thing would be decreasing? You've got n over e to the n, right?
The denominator is always bigger than the numerator.
Okay, yeah. And the denominator, it's not just bigger, but it's growing much faster. That's the point, right? That the denominator is e to the n grows really fast. e to the n goes really fast. Is what I was hoping to have. Okay. Okay. So yeah. So sorry to pick on you. Okay. So here's one way to see it a little bit more mathematically. You'd say, well, look. Here's a function that agrees with my sequence, right? This function agrees with my sequence at the natural numbers. Okay. Now I want to see that this function is decreasing. How am I going to see that this function is decreasing? By taking the derivative, exactly. Right? So you say, okay. Right? So you say, okay, well, what's the derivative? The derivative of a quotient is going to be bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. Right? And I can factor out an e to the x out of the top and the bottom. I get 1 minus x over e to the x. Mr. Allen.
Yeah, question, maybe too simplistic. What I did, I divided the preceding times the following.
Sure, that actually.
I reasoned that if it is less than 1,
Yes. That will.
Is that wrong, or-
No, that's perfectly fine.
Oh, okay.
That's perfectly fine. Yeah. So that's what we did that's kind of what we did in the first one.
yeah,
Right. Yeah.
okay.
That's perfect.
Something
That's perfect.
reversed, yeah.
Yeah. I just want to use the derivative in this one where I couldn't have used it in the first one. Yeah. Okay. But yeah, no, that's perfectly fine. Okay. So here you say, okay, well, look, the derivative, as long what I notice about the derivative, is it positive or negative? Well, the denominator is what? Positive? Negative? Positive, right? E to the x is always positive. 1 minus x, as long as I'm bigger than 1, then this is always going to be negative. Right? So you see that, as long as I'm slightly past 1, then this is always going to be negative, right? And so what you see is that this thing is a decreasing function past 1, right? So at 1, the slope is 0, but then past that, the slope is always negative. Okay, and that tells you that the sequence must have been decreasing.
Question.
Yeah.
Can you explain the derivative again? Like when I looked at
Let me get to you after because I want to introduce one more idea. Okay, cool. Sorry. Let me stick around for a minute after.
Is it strictly decreasing?
It is actually. It is. Yeah. Yeah. Okay. Let me just say one more thing. Let me introduce one more idea. Okay. So there's one last thing in this section. It's called the monotonic sequence theorem. Okay. Okay. And it says the following. So remember, we had said that if the sequence converges, then it's bounded. Right? If the sequence is convergent, then it's bounded. Right? But we found examples that showed that the converse was false. Okay. The reverse direction wasn't true. Okay. The monotonic sequence theorem says if your sequence is monotonic, then the sequence converges, implies the sequence is bounded, and also the reverse. If you're bounded, then your sequence converges. So here's the picture. What it's saying is that if you have an increasing sequence, so to be a little bit more careful about it, what it's saying is that if you have an increasing sequence, and that sequence has an upper bound, then it's going to converge to something. There's got to be some number L that your sequence converges to. Okay. Right? If your sequence is a monotonic, right? Monotonic increasing, and you have an upper bound, then your feed sequence is going to converge. Okay. Or, if you have a sequence that's decreasing and you have some lower bound, right, then your sequence is going to converge. Okay. Okay. That's what the monotonic sequence theorem says. Okay, so, and we're going to use it. So I'm not going to explain it, but we're going to use it. Just one example, if we look at this guy here, this is a decreasing sequence, right? This is a decreasing sequence, and it's bounded below by 0, right? All these terms, right? We just saw that a sub n is strictly decreasing, and further, a sub n's are greater than or equal to 0 for all n. Right? So the monotonic sequence theorem says that this sequence converges. Okay. It doesn't tell you what it converges to, but it tells you that it converges. Okay. Our first example also, 2 to the n over n factorial. Right? That was a decreasing sequence, decreasing and bounded below by, again, 0. Right? And so this guy's also going to converge. Okay, so our first example and our second example, we can use the monotonic sequence theorem on. Let me say one thing that may or may not be interesting to you. The monotonic sequence theorem is actually something very special. It doesn't work if you're in the rational numbers. If we were back in the world of Pythagoras and using rational numbers, you could have a sequence that increases and has an upper bound, but never converges. That's kind of strange. But you can think like this. If you look at the sequence 1, 1.4, 1.41, 1.414, 1.4142, blah, 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 these are rational numbers, and they're heading upwards secretly towards the square root of 2. But there is no square root of 2 in the rational numbers. There's just a hole there, right? And that's what happens in the rational numbers. So you'd have an upwards converging, you have this sequence going upwards, you have an upper bound, but there'd be this hole in the numbers that you would never converge to. Okay. So there's something unusual about the real numbers that you won't get to until later. Okay, that's it for today.